Swayam Prabha. Digital India. Educated India.
See, in the last class we have learnt what is strain at a point. When you say strain at a point, you recognize that you have to refer to state of strain at a point. And when you look at in two dimensions, you have three components. Fine. And we have also looked at, when we talk about infinitesimal strain, the quantity was very, very small. We are talking about in terms of micro strain, and we said it is 10 power minus 6 millimeter per millimeter. It's a very small quantity. So, you should recognize when we want to make strain measurement, you should be sensitive that we are going to measure very, very small quantity. And you have used a scale for measuring length. You have also used a vernier caliper. You have also used a screw gauge. You must have done it. And scale, you can measure 0.5 millimeter reasonably well. When you go to a vernier caliper, you can go down to 0.01 millimeter. When you go to screw gauge, you can go down to 0.001 millimeter. But you also find the range with which these measurement methodologies can be used, they also keep reducing. So, in any measurement system, you have a resolution. If it is of very high resolution, the range is also limited. Is the idea clear? And you have to be sensitized that we are attempting to measure the quantity strain which is extremely small. And in the Gudgeon pin we have put square grid, and then we have been able to see after deformation beautifully the deformed lines, and that comes under grid methods. Then you go to geometric moire. What they have done is, if I view the square grid with a master grating, that is what you have here, you have the master grating here, I have these black and white fringe patterns are seen, which is by mechanical interference, which has the ability to magnify the deformation. And the fineness of the technique depends on how many lines per millimeter that you draw. So, you have variation. I have a geometric moire, that is what is shown here. And when you say geometric moire, this graph brings out on the x axis the level of strain. The idea is, like in your measurement scenario, when you use a scale, when you use a vernier caliper, when you use a screw gauge, your resolution keeps improving and the range also getting smaller. So, when we go for any experimental measurement, they are applicable only for a particular range. Grid is a very crude way of finding out the strain. When you have very large strain, the grid is capable of showing good distortion. So, you are in a position to have an idea of what way the body is strained. Okay. The next step is you go to geometric moire. I view the square grid with another square grid which is called a master grating. Because of mechanical interference of these two grids, you have improved the accuracy. That comes under the category of geometric moire. So, this can operate somewhere around 2% strain to somewhere around 13 or 14% strain. And you have, theoretically, you can have up to 2000 lines per millimeter. It is very, very fine. And that comes under the category of Moire interferometry. And this Moire interferometry can start from something like 0.05% strain, and then it can go up to just before yielding. And you have a very new technique which is called digital image correlation, which works from near yielding to near breakage of the specimen for a very large range. And we have also looked at photoelastic coatings, and in the reflection scenario, you have the coating bonded onto a specimen. So, the strain from the prototype or the specimen is transferred to the birefringent coating. So, it is strain induced and you get beautiful fringe patterns. So, you have photoelasticity which is in this range, complete elastic range from almost close to 0 strain to till yielding. Then you have brittle coating. We have said that we will spray a brittle material, and it's very interesting. It's a brittle material, so when the normal stress reaches a critical value, you have cracks formed. So, in this technique, cracks are information. Normally, you are worried about the crack developed in any structure. Here, crack is used a measurement tool to find out what is the level of strain introduced, and it is used in conjunction with strain gauges. That is what we are going to discuss in detail. So, the idea is you can minimize the number of strain gauges if you know what is the direction of the principal strain at that point of interest. So, the brittle coating requires some level of strain. It cannot work below 500 microstrain. From 500 microstrain, little after yielding it can work. See, I have shown the stress strain curve for mild steel just for illustration. The focus here is when I go for measurement, there are multiple measurement techniques. Many of these techniques operate in a particular range. You should know what is the range of strain that you can use. And the advantage of strain gauge is it can work from almost close to 0 strain to somewhere around 12 to 13% of strain. And you also have another very interesting technique called thermoelastic stress analysis, which works from 0 strain to about 20 to 20%. It's a very, very expensive technique. The physical principle is when the material is stressed, the temperature at the point changes. So, you need infrared cameras to find out the temperature. It's a very expensive technique. So, this gives you an idea. You have multiple techniques. Many of them directly measure displacement. From the displacement, you find the derivatives and find out the strain. On the other hand, the strain gauge has an advantage that you have an electrical system that directly gives you the strain quantity. And many times, people say strain gauge gives me strain, which is a misnomer. See, what you will have to keep in mind is, I have a strain gauge which is blown up here. I have what is known as a gauge length. I want you to draw a sketch of this. And you have tabs where you connect it to lead wires. These are connected to the equipment for measurement. A strain gauge can give only a component of strain along the gauge length. So, that is what is summarized here. The gauge measures the axial strain in the direction of the gauge length. Do not say strain gauge gives you strain. It gives you only a component of strain, and it can basically measure only an axial strain. Okay. It has a finite size. It has a finite size, and you have a grid. And you have the end loops and solder tabs are considered insensitive mainly because I make them big. You know from your simple high school physics that when the area of cross section is larger and larger, the resistivity is small. Okay. So, you have a strain gauge where this element, we will also see in a short while how this is constructed. And when you say strain at a point, you may think that I want to measure at a point. We have gauge length ranges from 0.2 millimeter to 100 millimeter. So, you can't have a point. The minimum least length is 0.2 millimeter, but many of the common strain gauges readily available have a gauge length of 3 millimeters. If I go for 0.2 millimeter, it's going to be very expensive, and even the measurement technique has to be very sophisticated. So, the common strain gauge lengths are in the range of 3 millimeters, and you use 100 millimeter length on heterogeneous materials, because you would like to have an average of the strain over a length. So, you have to select what is the gauge length that is appropriate for your given application, and strain gauge selection is also a very important issue. And I want to caution, strain gauge is a widely used and abused technique. People abuse it because they don't have a formal introduction to what a strain gauge is, what are the sensibilities, because the electrical principle is very simple and straightforward. When you stretch a conductor, whatever the stress introduced influences the change in the resistance. But the resistance change also can occur because of change in temperature. So, in all strain gauge measurement, you must account and segregate any effect due to temperature. And when I say I have a strain gauge which has a finite length, and if I paste it on an area where the strain varies in a fashion like this, I have a peak strain here. Because I have a gauge length, it would only measure an average strain over this length. The average strain would be like this. So, if my average strain is smaller than peak strain, then this is not good selection of the gauge length for the given application. Is the idea clear? So, you will underestimate the actual strain coming on the prototype. At that point, see, you have looked at photoelasticity. When I had a model made of photoelastic material, I get information on all points in the structure. Such techniques are called whole field techniques. See, you need to know what happens in the neighborhood point. So, in one of the challenges in strain gauges, though it directly gives you component of strain, it is a point by point technique. You can get the information only where you have pasted the strain gauge. And when you paste the strain gauge, you should have selected the gauge length appropriate to the problem under consideration. If the stress state is uniform, no issue. If I want to paste it on a cantilever where the stress is varying linearly as a function of distance, average will equal to what is the strain at the point of interest. But when I have a plate with a hole, that is what we are going to see the next slide. So, what is a thumb rule in selection of gauge length? Suppose I want to put a strain gauge on the fillet, that is what is shown here. See, I have a tensile root fillet where you have also got a crack developed in service. And if you want to see in the compressive fillet, I have a fillet radii, and you will study in your machine elements course, if you want to reduce the stress concentration, one of the ways you try to reduce the concentration is providing a generous fillet wherever possible. So, the idea is you should have the gauge length not greater than 0.1 times the radius of a hole or the fillet. These are all thumb rules, you can only satisfy to the extent possible. See, other famous problem is your plate with a hole where you have stress concentration developed, and if I want to find out, these are all the places where you have maximum stress, and if I want to do this, I should have a selection of the gauge length depending on the size of the hole, and ideally I should bond it on the inner surface on the circumferential direction. Then make a measurement. Only then that measurement will give you the peak stress or strain correctly. So, gauge length is a very important factor that you will have to select. And if you look at the physics it's only high school physics. There is nothing great in this. And you all know the resistance of a conductor is R equal to rho L by A. Now I take simple wire. I want to find out how it is sensitive to the strain. Fine. Now I differentiate this, and then I have this as differentiate and also divide by R. I get an expression dr by R equal to d rho by rho plus dl by L minus dA by A. And you all know strain is nothing but changing length divided by the original length. Why do you have to study the strain sensitivity of a wire? We'll have to understand why do you make a strain gauge as a grid? Why you not have a simple speck of material to give you strain? That is one issue. Another issue is, see, when I want to paste a strain gauge in an object, a priori I do not know what is the level of strain. Is the idea clear? It can go from elastic region to plastic region. When I want to interpret the data from the strain gauge, whatever the calibration constant that I use, it should be same for elastic as well as plastic ranges. Otherwise, I cannot make a measurement. So, when I take a conductor and look at as a function of the specific resistance, as far as the geometry, I get a knowledge what should be my calibration constant, to what way I should tweak it so that I don't have a difficulty to move from elastic to plastic strain. Fine. Now we will simplify it, and we will also have to talk about what we have looked at in the simple rubber experiment. You know, we have looked at when I stretched the rubber, there was a contraction on the lateral direction. This happens at a fixed ratio, and that ratio is credited to Poisson. We will use that. Okay. So, we have the cross section, we have taken a circular cross section. So, the area is pi by 4 d squared. So, dA by A, I can write it as 2 dd by d. Now, I will replace it in terms of the axial strain, which we have looked at in the simple experiment, and this ratio is known as Poisson's ratio. So, I can replace what is dA by A in my expression in terms of this strain dl by L. This is all high school physics, you have learnt it, you know all this differentiation. I would like you to write down these expressions, these are very simple to use. And there is also a limiting value of Poisson's ratio, we will see that in the next class. It will go to 0.5 when the material becomes plastic. Okay. So, when I substitute this in the expression, I get this as the strain sensitivity SA is defined as dr by R divided by dl by L. When I substitute for dr by R in terms of the specific resistance and the other quantities which we have evaluated, I get strain sensitivity of the wire. It is not the strain gauge. Strain gauge is made out of a grid. Strain sensitivity of a wire equal to d rho by rho divided by dl by L plus 1 plus 2 nu. So, when the material becomes plastic, then value of nu goes to 0.5 and the first term goes to 0. So, this goes very close to 2. So, if I have the calibration constant, when I have to find out from the resistance change how to get the strain values, if I have that closer to 2, then I can comfortably go from elastic range to plastic range. So, that knowledge you get from this. And people also have developed, see, I said it is very difficult to get a speck of material for me to make the strain measurement. If I not get speck of material, at least I should have the shortest length possible. What is the way that you can have the shortest length to have a highest resistance? One way is you develop alloys which have high specific resistance. Don't use copper. they use copper nickel alloys, which are called constant and advanced, which have very high specific resistance. That's one way of doing it. What is the other way of doing it? You know, resistance is rho L by A. So the other way of doing it is reduce the cross section to the least possible. With all those calculations, people have found, even if I want to have 100 ohms as the base, as a resistance, I need about 100 millimeter length of the wire to do it. Because if I have higher and higher resistances, any small change I can make the measurement. See, one of the challenges when they discovered strain gauge was how to measure microvolts, because I am going to have micro strain. So the electrical change also will be in very small quantity. So people needed amplification circuits for them to have measurement of this very small voltages. You have to recognize that is 10 power minus 6. I do not know how many of you have gone with your mother to go and buy gold. Have anyone gone? We have girls here, at least boys have not gone, at least girls should have gone. Have you noticed, buying gold is one aspect. Have you noticed how he weighs it in the shop? He has a balance, he closes that balance, he doesn't even want an air current. And you are measuring gold in terms of grams. Is the idea clear? And here you are going to make a measurement which is 10 power minus 6. We have not measured anything like that in our life earlier. So you should be very sensitive to that. Okay. How many of you are from North India here? Raise your hands. You all use your heaters in your winter? You have electrical coil? Am I right or not? Have you seen it? At least you would have seen it. And it generates lot of heat and provides you warmth. Now I have a very small tiny strain gauge. I am going to pass current through this. This also acts like a micro heater, I squared R. Loss is there. Because I am going to measure 10 power minus 6, you can't feel the heat. In a domestic heater, it is 1000 watts. This will be very small wattage, okay, 0.04, 0.06 or something like that. But that heat generation also affects your electrical response. So you have to be very sensitive that you are measuring extremely small quantity. Never forget that. So what is a gauge construction? So you have to make a strain measurement using a long wire, and you have a photo grid which is made very large. So they take pains to make the strain gauge grid like this. And these are all done in metal foil, and what you have is you have a straight line portion. We have already said that we are going to measure strain along the gauge length, fine. So I ensure that my design is also such, I have sensitivity high along the axial direction, and wherever I have loops, I have made the loops very thick so that it has comparatively lower resistance. And I have this for taps, and very carefully you make the strain gauge made of a very thin metal foil. Even though it is made of metal, you cannot go and take it on your hand, you have to take it through a tweezer. I will show the strain gauge towards the end of the class, okay. You have to, otherwise it will become, it will broken, it will get broken, and when you connect it, it will not show any reading, okay. And it is like a basic resistor. How many of you have played with your electronic circuits? Have you constructed any electronic circuit in your school or your fun? You go and buy resistance in a shop, electronic shop. You get resistance of all values. Strain gauge is also a resistor, but it is not available in all values. It is available only in specific values. And I have said even making 120 ohms is very difficult. Now you have 350 ohms, 500 ohms, 1000 ohms and 3000 ohms. Please write down this number. Numbers are very important. See, in engineering, certain numbers, certain appreciation. When I say that calibration constant, what I am looking for should be close to 2. Never forget that. And when you go and look at a strain gauge, the basic one, we said that even if I want to have 100 ohms, I need a long wire, and the standard strain gauge, the least resistance that is available is 120 ohms, and it is a technologically influenced technique. As the technology has evolved and you have finer and finer measurements possible in strain gauge, with the technology right now, you can confidently measure 1 micro strain. No other strain measurement can give you this accuracy. But if you want to get this accuracy, you have to select the strain gauge properly. You should be sensitive to what the heat generation, how the heat is dissipated. Now we are in a world where we are bombarded with composites because we won't have weight reduction. What is the difference between a composite and a metallic structure? Because I have been talking about heat. Can you tell me it's made of plastic? You have studied in your physics, thermal conductivity. Am I right? How do you expect a plastic to behave in compared to metal? Metal will dissipate heat fast. Plastic is not going to dissipate heat. So when I going to work with composites, please use a strain gauge which is of 1000 ohms. Why? What is the loss when the current goes in a conductor? I squared R. If the voltage is fixed constant and if the resistance is very high, you reduce the current flow. So you reduce the heat generation. You reduce the heat generation because you know you are going to work on a material which is not going to dissipate away the heat as efficiently as like a metal. So many times, many laboratories, what they do is they make the strain measurement with the available strain gauge without paying attention to on which material they are working on. So you have to select, like I said, that you have to select the gauge length. You should also select the resistance of the strain gauge. It's not trivial. It's very, very important. Having said this, now I have a grid. Obviously, since you have studied what is state of strain at a point, and you have also looked at from a photoelastic experiment how the strain field is in the form of fringes. When I am going to have a finite grid like this, it is going to be sensitive to the axial strain, transverse strain, as well as shear strain at the point. Let us look at what way we have handled this. Okay. So in this language it is put epsilon A is axial strain, that means strain along the gauge length. Epsilon T is the strain perpendicular to this, transverse to the gauge length, and gamma AT is the shear strain in the plane of AT. So I can write this change in resistance by R with 3 factors. See, when I was talking about a conductor, I put capital A. When I am talking about a strain gauge, the axial response, I put it as a S suffix small a. So it is sensitive to epsilon A, it is sensitive to epsilon T, as well as sensitive to shear strain. But because the way I construct the gauge, I can neglect the effect of shear strain, but I cannot neglect the effect of transverse strain in critical applications. Okay. So what I have is, this expression is simplified to dr by r equal to SA multiplied to epsilon A plus KT into epsilon T. And KT, you call that as a transverse sensitivity factor, which is the ratio of ST by SA. That is axial sensitivity of the strain gauge and transverse sensitivity of the strain gauge, the ratio of the transverse sensitivity to axial sensitivity. We saw what was there for a simple wire. From the wire, we have graduated to a grid, and we have seen grid is unavoidable. And a common gauge length, what you have is only 3 millimeters. That is what is available cheap. Even the cheap strain gauge will cost you $10. So it's very, very expensive. It is $10 to $1,000 or $3,000 one strain gauge. So it's a very expensive measurement technique, but very accurate. And what do the manufacturer gives you? Manufacturer generates strain gauges in a batch and selects few of them, conducts a test and gives you what is known as gauge factor Sg, which is defined as dr by r equal to Sg multiplied by the axial strain. So, from your electrical measurement, you will be in a position to get dr by r. From the manufacturer supplied value, you have the gauge factor Sg, and in IIT, in your strength of materials lab, you have an experiment using strain gauge to measure the strain in the case of a cantilever, and also for a torque measurement in the case of a twisting of a shaft. So, if you recall, you would have the gauge factor around 2. I have already given a reason why it should be around 2. And it's so fortunate the manufacturer simplifies your exercise. He has done a calibration in such a manner, by using this expression you directly get the axial strain. And if you have to incorporate transfer sensitivity factor, you have methodologies developed. People also use such sophisticated improvements on the basic measurement available as a software. How do I measure this small quantity? This is again, you have done it in your high school physics. So, draw the Wheatstone bridge, and we exploit the Wheatstone bridge to the hilt in strain measurement. See, we have already seen. I want you to draw the sketch, make the sketch. We have to find out, because we are going to get one very important expression that will help us to amplify my signal with minimal effort. I have also said you have load cells, even a vegetable vendor these days have an electronic balance. Am I right? How do these electronic balances operate? They all have a strain sensing element, which is basically a transducer where you have strain gauge pasted on a appropriate spring element. And when I use it as a transducer, my focus is to measure the weight accurately. So, in order to get the signal properly, I would like to amplify the signal. There is a difference between strain measurement and a transducer application. In a strain measurement scenario, whether the strain is small, my strain gauge should be able to give me the value. In a transducer application, in order to improve the accuracy, I would like to maximize the signal. You will learn from the construction of the strain, the Wheatstone bridge. Okay. So, I can write VAB equal to R1 by R1 plus R2V and VAD as R4 by R3 plus R4 into V, and I get this voltage drop across the point dB as given as R1 R3 minus R2 R4 divided by R1 plus R2, and you also have in the denominator R3 plus R4, and the bridge is initially balanced. I have R1 R3 equal to R2 R4. So, one thumb rule is you make these resistances R1 R2 R3 R4 equal to start with, and you make the null balance measurement, which is very, very accurate, and you have to keep in mind that we are measuring extremely small changes, which we are not accustomed to it. Fine. So, you have to understand every aspect is important. And when I write this final expression, okay, I have a very interesting relationship which tells me how I should use the arms of the bridge effectively. The change in voltage is related to V multiplied by R1 R2 divided by R1 plus R2 squared. This is more or less a constant for a configuration if I have selected the voltage. I have label this as in clockwise direction R1, R2, R3, R4. Even this is very important. And when I look at this expression, I get this as delta R1 by R1 minus delta R2 by R2 plus delta R3 by R3 minus delta R4 by R4. So, I would use this change in sign appropriately in my design of the spring element. And the way to understand this, when I have labeled this like this, opposite arms add, okay, because I have delta R1 by R1 plus delta R3 by R3. Adjacent arms R2 and R4, you have that subtraction. So, I have also connect two strain gauges and a Wheatstone bridge and make the measurement. This should have one sign of strain, this should have opposite to that. Only then it will add. If they are of the same sign, you will get only 0 as the answer. I can also have another configuration, I can have all 4 arms connected as strain gauge. Either you can have a single strain gauge, 2 strain gauges, or only 4. You do not have anything with 3. You cannot make any measurement with 3. I have a very interesting application. I have a cantilever beam. And then I apply the load here, and then I put a strain gauge on the top. I put the strain gauge at the bottom. Even though we have not formally studied what is the variation in a beam, I have already shown it schematically. Do you recall what was the strain variation or stress variation? It is maximum at the top fiber and least at the bottom fiber of opposite sign. Okay. So, I have pasted one strain gauge on top, one strain gauge at the bottom. When I connect them in the Wheatstone bridge like this, I amplify the measurement of whatever the signal I get, I amplify. So, my measurement of force becomes more and more accurate. If I suppress noise, amplify signal, my instrumentation system will give me reliable values of the force. That is my interest. Suppose I have a system where I have a cantilever, I have put 2 strain gauges and I have connected like this. What do you anticipate? Tell me, you have just now looked at what way the Wheatstone bridge behaves. And you know I have put strain gauge 1 here and strain gauge 2 here, both are in the top surface, both are experiencing same signature. You will be coming and telling that this is a very strong beam, nothing happens to the beam is what you will conclude. Whereas you have done a mistake in your measurement, because any load I put, I will get only 0. Is the idea clear? See, in a sense, you also learn application of your knowledge of stress and strain in this measurement also. I have taken a shaft under torsion. I have shown I have taken a shaft and I have twisted it anti-clockwise. Can you sketch what is the state of stress? Suppose I take a point here, okay. You tell me what way it is twisted. You have in front of you, I put a point in front of me, I put it anti-clockwise. Can you sketch the state of strain? It is a pure shear strain. Can you sketch the direction of strain and then check with my diagram? First thing is you should know how to find out what is the load applied on the system. So, you take a square element, draw the strain acting on that or stress acting on that, whichever way you can do it. Make a mistake, no problem. And I have already told you a strain gauge can measure only axial strain. The question here is, how do I use my strain gauge to measure what happens in torsion? What way do I have to align my strain gauge when I want to make the measurement? That is also very important. In strain gauge instrumentation, all these aspects are important. What should be the size of the gauge length, what should be the resistance, and what way I should align my strain gauge. Have you figured out the stress, what is happening on the element? I have this as in the negative direction because I am putting it anti-clockwise. I am putting a point in front of me. Okay, when I put a point in front of me, it will appear one way. When I put on the other side, it will appear the other way. This is what I am looking at. Okay, which you can visualize. Once you have drawn this, you have already studied Mohr circle. And when you are dealing with an isotropic material, in an isotropic material, whether I have stress state and strain state, they are identical. Your principal stress direction will coincide with principal strain direction. With that knowledge, can you visualize this as combination of axial strain? A pure shear stress state is introduced. Can you go to Mohr circle? Can you draw the Mohr circle for this? Draw the Mohr circle for this and find out at what angle you have the principal stresses. It is an application of what we have studied earlier. It is nothing new. Please draw the Mohr circle. I will draw the Mohr circle for you now. Okay, before the Mohr circle I have drawn this. Okay, let us see the Mohr circle. I have the Mohr circle drawn like this, and I have these two are the points where you have the maximum normal stress. They are the principal stress direction. They are also the principal strain direction in the case of an isotropic material. And this is located at 45 degrees. So I have it in clockwise. So when I rotate clockwise, I have this as maximum stress, which is tension, which is also the value of tau. So I have tension. So that is why your element is stretched like this and compressed the other way. And if you look at from a diagram like this, I can write an equivalent stress state in this fashion. Is the idea clear? That is important for you to recognize. How do I use my strain gauge to find out what happens when the object is undergoing a pure shear stress state? So it tells me that I have to align my strain gauge this way. So when I see the side view, I will put one strain gauge on the top. I will put the other strain gauge. We have put this as 1, 2, 3, 4. Okay. This is experiencing. I have this direction. Okay. This is if I say this as 1, I will say this as 3, whichever way. Okay. So I put this on this surface. I put this on the other side. Okay. And this is oriented at 45 degrees. So similarly, I put two other strain gauges that measures the compression. So I can measure only axial strain. Fine. So we don't give up. And you know from stress analysis what is a stress state there. From your Mohr circle, you have an understanding. It can be visualized as combination of tension and compression. And then when you do this, you also recognize epsilon 1 and epsilon 3 are positive, epsilon 2 and epsilon 4 are negative, and connect them appropriately in your Wheatstone bridge. Don't connect it wrongly. I will put this as 1, 2, 3, 4. So they all add up. So when I do this, I get 4 times the signal. So if my interest is to find out torque, I said that you have to use a torque wrench when you want to tighten the bolt. So when I want to have a torque wrench, I should have a system to measure the torque and give you that as a reading. So there are many instances where you have to find out the torque. So it is a transducer application. Your intention is to find out the torque applied. So you design a mechanical element, spring element, in which you place more than one strain gauge and connect them appropriately so that you amplify the signal. So I can make a torque wrench using this as a strain sensing element, and I can amplify my signal. And the moment I say from stress analysis point of view, I want to find out strain at a point. When you say strain at a point, you are looking on a plane surface, okay, that is you have a free surface on which you want to measure. You have 3 quantities, epsilon x, epsilon y and gamma xy. So when I want to measure 3 quantities, I need minimum of 3 strain gauges. You get my point? I have a strain gauge 1 at oriented at theta A, strain gauge 2 oriented at theta B, strain gauge 3 oriented at theta C. I told you transformation laws are very, very important. You cannot afford to forget it. You should be able to write them very comfortably. Fine. You find an application in the case of strain gauges. So I can go and find out what happens, and thankfully the strain gauge manufacturers puts 3 strain gauges in a backing and supplies you, and this is called as a rosette, because aligning it on a field is extremely difficult. You have pre-aligned strain gauges. So whenever somebody says strain gauge gives you strain, don't say that. It gives you only component of strain. A strain rosette which has 3 elements in it can give you state of strain on a 2-dimensional situation. Okay. And the reason why I have put this is, you should have written this transformation law. This is nothing but x prime x prime. Okay. Epsilon j, what is indicated here, is nothing but x prime x prime. That is given as epsilon xs cos squared theta, epsilon yy sin squared theta, gamma xy sin theta cos theta. So you have to use this and then extract the value of strain at the point of interest. See, you have a physical difficulty. I have to have 3 strain gauges and I have to find out what is strain at a point. Let us see how they have constructed the rosettes. You have a very famous rosette called a rectangular rosette. I have strain gauges mounted like this. So you deliberately make an approximation as if these strain gauges give strain at the point O. So there are engineering approximations involved in strain measurement, and you may make the strain gauge as small as possible. You also have strain gauge where they are stacked one over the other, so that the center of the strain gauge forms at this point, but you amplify heat generation 3 times. So you should have very positive way of taking away the heat. So your measurement should be sensitive to that. You may not have the luxury, so you have this. And when I have a strain gauge like this, this is called as a rectangular rosette, and you have this angles as fixed as 0, 45 and 90. You can apply the transformation law and tell me what is epsilon A in terms of epsilon x, epsilon y and gamma xy. So the idea is to find out epsilon x, epsilon y and gamma xy from the measurements of strain along direction A. When I put the strain gauge as A, I can also say that strain along direction A, strain along direction B, strain along direction C. And when you simplify, I get epsilon x is identical to epsilon A. Epsilon y is identical to epsilon c because I have aligned it along the reference axis x and y. And gamma xy comes as 2 epsilon b minus epsilon a minus epsilon c. It is very simple and straightforward. There is nothing new. It is all high school physics. But what you have to keep in mind is, technologically strain gauge measurement is very, very sensitive. You need high precision strain gauges. And how do you bond them? How to bond a strain gauge on a given surface on a prototype itself is a very important training as a strain gauge measurement specialist you have to undergo. And there are certificates given by British Society of Strain Measurement. You have to renew that certificate every 3 years. So it's not a simple job. It's not that anybody can walk in and take a strain gauge available, put it on any substrate and then make the measurement. That is why I say it is abused. If you know the technique, you should select the strain gauge, follow appropriate procedures to bond and then make the measurement. I also have another variation which I am not going to spend much time. You have a variation like this, you can work it out. Okay. Now, if I go to strain gauge manufacturers, they have an elaborate list of strain gauges available. Okay, there is a designation system. I want you to write one of this, okay, just write this, because you should know all these parameters need to be selected for a given application. I should know what should be the foil alloy, I should know what is the backing, how on what substrate this strain gauge is put, okay, and there is also something called temperature compensation number. You know, some alloys are made, if there are small changes in temperature, this itself can annul that. I can have just one strain gauge connected to the Wheatstone bridge for a range of short range of temperatures, it can cancel the temperature effects. And what is the gauge length? Because the gauge length is very important. You can't say I will always use 0.2 millimeter. It's so expensive and very difficult to do. Okay. And what is the way I should have the grade? Because it should help me to provide the access. And what is the resistance? I said in a composite, please use 1000 ohms, at least 500 ohms, never use 120 ohms. And there are many options available. Okay. And these are the two people, one is the Vishay Micro Measurements, another is HBM. They are the people who are dominating the strain gauge. And they have a different system. Okay. So you should know, if you are using, there are thousands of configurations available. So you have to select appropriately the strain gauge suitable for your application and then use it. And I would also like to show, it's a very precious, I said it is not cheap, it's available in a very nice packet like this. You have a small strain sensing element. I cannot go and take it with my fingers. I have to use tweezers, okay, and then go and take it out. I must handle it very delicately. If I handle it roughly, the strain gauge is gone. Once I paste the strain gauge, I cannot reuse it. Is the idea clear? Even though it is made of metal, it's a very thin film to have very high resistance. So I should handle it very carefully. It is very expensive. Okay. Then there are also, from measurement perspective, what all that you require. Whether I need a single element strain gauge, whether I need a row set of 2 or 3, all that you have to look at, whether I am working in a biaxial stress field, whether the principal stress directions are known. So, we have looked at what is brittle coating. In the brittle coating, when I have a crack pattern, I said tangential to the crack and perpendicular to the crack, you know the principal strain direction. When a principal direction is known, I can paste just one strain gauge for me to make the strain measurement, or 2 strain gauges. See, at a point I need 3 strain gauges. If I need 3 strain gauges, I need 3 instruments to measure the strain. Is the idea clear? 3 Wheatstone bridges are required. If I reduce one component of strain not to be measured, I can go to brittle coating and then align it along the principal directions. It's enough I put only 2 strain gauges. I can use a T row set. So I reduce my measurement requirement. And in a generic situation, I should use a delta rectangular row set because I need 3 components of strain. So whether I use a single element strain gauge, 2 element strain gauge, or 3 element strain gauge, also a decision you have to make. Because when you go to a point by point technique, how many points I make the measurement is going to decide my design of the component once I get the measurement. I have a limitation in the capacity of how many points I can handle or how many channels I can handle. If I have 3 strain gauges, it occupies 3 channels. If it is 2 strain gauges, it occupies 2 channels of my measurement system. So if I have a 1000 channel system, if I want to increase my number of data points, you should not say, I will simply use, I have enough money to spend, I will simply use row sets at every point. Then you can't make best out of your experimental measurement. Some places you may have to use single or 2 elements so that I can make large number of measurements. So this is a difference between a whole field technique and a point by point technique. And the rudder of a Concorde aircraft was failing very repeatedly. They had done a finite element analysis, they have also pasted a strain gauge, still the design was not improved. Only when they pasted a photoelastic coating and made the measurement, they found they pasted the strain gauge slightly off from the peak strain what they had actually got in the structure. So that failure was prevented only with the help of a whole field technique. So with this you have a bird's eye view of what a strain gauge technique is. A strain gauge can give you state of strain at a point provided you use a rosette. And strain gauge has to be selected appropriately for a given application. Always keep in mind you have to look at the thermal effects. You should know how to cancel it. You can cancel it electrically by having two strain gauges on adjacent arms, experiencing one experiencing the actual strain, other experiencing the ambient temperature, or you use self temperature compensated gauges, and select an appropriate gauge for a given material. Don't simply use what is the strain gauge available at the 11th hour you plan and then try to make measurement and finally blame the technique that the strain gauge technique is not giving you correct results. It's a very sophisticated technique. You have to be sensitive from the first stage of the experiment and handle the technology, listen to all the manufacturer's recommendation, pace the strain gauge and make the measurement. Thank you.